Today we're going to talk about 13.2 and the general angles that are formed in trigonometry on a 360-degree plane and how to measure their angles in radians. So first of all, I'd like to talk to you about what is considered the standard position of an angle. In standard position, it is an angle whose vertex is at the origin and the initial side is on the positive x. So if we look at this red angle, we have the initial side coming from 0, 0 out, and then we have the terminal side, the place where the angle ends, coming out. If we look at a 360-degree plane, this would be 0 degrees, up to 90 degrees, to 180 degrees, to 270 degrees, and back to 360 degrees. So every angle's initial start will start with 0, 0 and draw your initial vertex out towards 0, 0. Any angle from there within will have their terminal side anywhere in this area. You need to understand that positive angles will always go counterclockwise. So this red angle is a positive angle because it starts here and goes towards the counterclockwise position, where all negative angles will go in a clockwise position, like this. So here, this blue angle is positive 130. It starts here and goes in a counterclockwise position. This negative angle of 75 still starts at the same place, but it goes clockwise in the direction of a clock. 12, 1, 2, 3, 4, 5, 6. This is clockwise. Heading backwards would be counterclockwise. I also would like to talk to you about coterminal angles and quadrantal angles. A coterminal angle, they have the same terminal side. For example, right here is my angle. So I first have an angle, and it looks like about 130 degrees. And then when I come around another full 360, that would be a coterminal angle. So this one says 135 degrees, plus another 360 would be 495. If I went around again, another 360 would be 855, etc. Also coterminal would be in the negative way. So if I came this way around, it is also coterminal to the 135. Up to this point would be negative 90, negative 180, negative 225. So it means they have the same terminal side. They end in the same place. Just to refresh your memory, quadrants. We have our coordinate plane. This is quadrant 1, quadrant 2, quadrant 3, quadrant 4. The quadrants should make a C for coordinate plane. I'm going to have you draw a few angles. So make your XY axis. On the first one, on A, would you draw negative 120 degrees? So again, I start at my 0, 0 and go out for my initial side. To go negative, I must go clockwise. So this far would be 90, and then I would need 30 more. This is negative 120 degrees. And I would like you to put in those angle representations to show me what direction you are going. On this one, I'd like you to do 400 degrees. So again, I start with my 0, 0 and come out towards 0 degrees. All the way around here is 360. So I would need 40 more degrees. So this entire angle is 400 degrees. Notice the difference. Here I went counterclockwise, here I went clockwise. This way I am going counterclockwise. Okay? This time we're asked to give a positive and a negative coterminal angle, first of all, to negative 100 degrees. Well, if I'm going to go positive, I'm going to have to add 360. That would bring me to 260 degrees. This would be a positive coterminal. If I would go more negative, I would subtract 360. And that will give me a negative 460 degrees. That would be two coterminal angles. Let's try B. I'm at 575 degrees. So to go more coterminal, I could add 360. That would be 935 degrees. To go negative, I would subtract 360. That's still a positive 215. So I'm going to have to subtract 360 again. That brings me to negative 145. There I have one negative and one positive. Now in this case, I could have also said positive 215 would end at the same place too, and then subtracted another 360. So it just depends where you're at. But to get positive coterminals, add 360s. To get negative, subtract 360s. And you may have to do it more than once. We're used to our angles being measured in degrees. However, as we continue with our trigonometry, we find out they can also be measured in what's called a radian. How you get a radian let me show you this little video clip. A radian is the radius wrapped around the circle. So one radius wrapped around the circle gives me a radian measure in here. So since a circle see how it's wrapping around there? And to get how many degrees it is, we know that there are 360 degrees. So we would have, let me show you. Equals 2 pi r. which is the circumference of a circle. So if I take that radius and keep wrapping it around, if I want to find what the radius is, it's the same as the radius. So I would divide by 2 pi. 360 divided by 2 is 180. So I get 1 radius, or 1 radian, is 180 degrees over pi. So then, to get a degree, I go backwards and I flip this. 1 degree is pi over 180 degrees. And you're going to use that to convert from degrees to radians. So if we have 320 degrees, 320 degrees is equivalent to how many radians? Well, we're going to have to take our degrees and multiply it. We either multiply by 180 degrees over pi or pi over 180 degrees. And since we want the degrees to cancel, we want the 180 degrees in the denominator. So it is times pi over 180 degrees. Notice then your degrees cancel. Your zeros also reduce a 10. Then I see that there is a 2 in each. 2 into 32 is 16. 2 into 18 is 9. 16 and 9 no longer reduce, so in my numerator I have 16 pi, and in my denominator I have 9. So 320 degrees is equivalent to 16 pi over 9. Radians will always be named in terms of pi because of this formula, circumference. So how about if you have negative 5 pi over 12? Well, the negative just means I went in the the clockwise position. So I'm just going to take the 5 pi over 12. And I'm either going to multiply by 180 degrees over pi or pi over 180 degrees. Well, if I'm converting to degrees, I want my degrees in the numerator, and I want my pi in the denominator, so that the pi's will reduce. So the pi reduces, and 12 and 180 reduce. To 15. So I have 5 times 15. And I get 75 degrees. We can try another one. Let's see what 200 degrees is equivalent to in radians. Well, it's degrees, so I need my 180 degrees in the denominator to reduce out. So the degrees and the degrees reduce. The tens reduce. And 20 and 18 both reduce by 2. 2 into 20 is 10. 2 into 18 is 9. So I get 10 pi over 9 radians. Oh. Down here I forgot to put my negative 75 on because it was a negative angle. Right? So let's say we have 5 pi over 6 radians. How many degrees is that? So I start with 5 pi over 6 times, where's the 180 going to go? In the numerator or denominator? I'm changing it to degrees, so I want it in the numerator. I want my pi in the denominator, so that my pi's will reduce. So your pi and your pi reduces. 6 goes into 180 30 times. So I have 5 times 30 is 150 degrees. So how about if we're asked to evaluate our trig functions that we learned yesterday when we're given in radians? Well, sine of pi over 6. Well, pi over 6 is how many degrees? So you're going to, I want the degrees, so I put it in the numerator over pi. The pi's reduce. 6 goes into 180, 30. So this is equivalent to the sine of 30 degrees. So again, I can put my theta here. Opposite of a 30 is 1. Square root 3 and 2. Opposite your 30 would be 1 over 2. So the sine of pi over 6 is the same as 1/2. Well, if I have pi over 4 times 180 degrees over pi. Your pi's reduce. 4 goes into 180, 45 times. So this is equivalent to the tangent of 45 degrees. So I'm going to make my 45, 45, 90 triangle. 1, 1, square root 2. So tangent, opposite over hypotenuse, opposite over adjacent is 1 over 1, gives me 1. So let's see if we can fill in this chart. Let's find the sine, cosine, tangent, cosecant, secant, and cotangent of all of these special triangles. So the sine of 30, opposite over hypotenuse, is 1/2. So then we know the cosecant should be the reciprocal 2. Cosine of 30 is adjacent over hypotenuse. Adjacent is square root 3 over 2. So the secant will be the reciprocal, 2 over square root 3. Now when I simplify that, I have to multiply by square root 3. I get 2 square root 3 over 3. The tangent of 30 is 1 opposite over adjacent. 1 over square root 3 would be square root 3 over 3. So the reciprocal, I'm going to reciprocal the original, would be square root 3 over 1, which is square root 3. So now, if I do it for 60 degrees, the only thing that switches is my opposite and adjacent. This is opposite, and this is adjacent. So sine, opposite over hypotenuse, is square root 3 over 2. So its reciprocal, cosecant, would be 2 square root 3 over 3. Cosine is adjacent over hypotenuse, so it's 1/2. So its reciprocal, secant, would be 2. And then tangent, opposite over adjacent, square root 3 over 1 is square root 3. Its reciprocal would be 1 over square root 3 or square root 3 over 3. 45 degrees. Opposite, adjacent. Sine, opposite over hypotenuse, 1 over square root 2 will be square root 2 over 2. Its reciprocal the first part, square root 2 over 1 is square root 2. cosine, adjacent over hypotenuse, 1 over square root 2, again, square root 2 over 2. So secant is the reciprocal, square root 2. Tangent, 1 over 1, which is 1. The reciprocal of 1 is 1. You're going to have to know all of these. You're going to have to know how you get them, because you'll have a quiz on these exact angles. The last thing I'd like to share with you is how to compute the arc length. Arc length from geometry is x degrees over 360 degrees times circumference, which is 2 pi r. X degrees over 360 degrees times circumference, which is 2 pi r. So we are going to substitute in our theta. It is theta over 360 times 2 pi r, because we don't know how many degrees that is. And as we know, this part reduces to 1 over 180. So pi over 180 is a radian. So we can say that these two would reduce each other out, because pi radians and 180 degrees reduce each other out. So the arc length is theta times your radius. So if we try a few, if we have a radius of 3 and a theta of 120 degrees, that's where we'll use x degrees over 360 degrees times 2 pi r. Well, I have 120 over 360 degrees times 2 pi, my radius is 3. Again, the degrees reduce, the zeros reduce. 12 and 36 reduce to 1/3 times 2 pi times 3. The 3's reduce, so I get an arc length of 2 pi. Let's see what the arc length of 210 degrees and a radius of 3 would be. So again, 210 degrees out of 360 degrees times 2 pi radius 3. Again, your pi's reduce, your zeros reduce. 3 goes into both, so I have 7 over 12 times 2 pi times 3. The 3 and the 12 reduce to a 1 and a 4. Then this 2 and 4 can reduce to a 1 and a 2. And I have 7 pi over 2. How about if it's in radians? If it's already in radians, then it is radius times my radians, 2 pi over 3. Nothing reduces, so I get 10 pi over 3 units. My radius is 8. My radians are 5 pi over 6. 8 and 6 reduce by 2. Nothing else reduces, so 4 times 5 pi is 20 pi over 3. should now be able to do your homework.